In this video, we shall see the equivalences or relations equations involving quantifiers. So we know that there are two types of quantifiers, there exist and for all. So using these two, we shall see what are the identities or equations that are true or which can result to false. So first one is there exists x such that p of x and q of x. So here we are saying there exists x for what condition? For this condition. What is the meaning of this condition? P of x and q of x. This whole thing should be true. When are these two true? When this one is true and this is true, because there is a AND condition. So we can say that suppose there are some p of x and q of x whose truth value is like true, true, false, 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 true, 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 false, 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 false. So this condition implies there exists x p of x and there exists x q of x. Is this whole thing true or false? We shall see. So if we from this table we can see the first part, there exists x p of x and q of x. If we do AND p and q, then only this one is true, others will be false. And there exists x, yes, there is only one condition which is true, so we can say that this whole condition is true. Now coming here, there exists x p of x, means does p of x has at least one true? Yes. Does q has at least one true? Yes. So this one is satisfied. Next, if we see the opposite, there exists x p of x and there exists x q of x. Does this imply or is equal to there exists x p of x and q of x? Is this true? I have simply exchanged the left hand side and right hand side of implies sign for second number. So here we are saying, suppose p of x is there, p of x is having true, false, true, true. Suppose it is like this, and then q of x has a true and rest are false. This is the condition. Is the left hand side satisfied? There exists x p of x, yes, at least for one we are having 3 here, p of x is true. And means this part is true, and there exists x q of x, yes, there exists at least one true, so this one is also true. True and true is true. Now this side is true. Coming to RHS, there exists x p of x and q of x. Now if I will do p and q, then all will result to false. So this one is becoming false. So this one is not the means this is not a equivalence. These are not equal. Since this is not implying this, we cannot write here equal to. Therefore this is only one sided. This from this we can say this is being done and not the vice versa. So next we shall see similarly for all x p of x, or for all x q of x Now this whole thing, does this imply for all x p of x or q of x? Is this true? We shall see. Okay, so here we are saying for this first left hand side to be true, we need to make either this one true or this one true. Suppose I am having p of x and q of x, where p of x is all true. Okay, we shall see what we shall take for q of x. Means this one is true. Since this is a OR condition, we need only one value to be true. So this whole left hand side is now true. Now if I will do OR, okay, if I will do OR of p and q, so here p or q, this will all result to true because this side is having all trues irrespective of values of q. So this whole thing will also become true, means RHS also becomes true if left hand is true. Now if I was not taking p of x as true, then I would have taken q of x as true, which will again we will reach at the same conclusion that this is a equivalence. Okay, similarly let's see if we can exchange and get for all x p of x or q of x. Does this imply for all x p of x or for all x q of x? Are these two both same or not? So here we can see if we have a p of x and a q of x such that this is true false true false, this is false true false true. Okay, suppose something this is the scenario, then if I will do OR p or q, then all will equate to true. This side becomes true. But for all x p of x, here all are not true, so this is false. Similarly here all are not true, this is also false. So we have a counter example for which this is not becoming a tautology or this is not true. So this does not imply this one, like earlier it was not implying, similarly this also does not imply. Okay, so now next, the last two are the common ones, that is there exists x p of x or q of x. This is equivalent of saying p of x or there exists x q of x. This can simply be proved without using truth tables also. Like we know for doing there exist, we do OR of all the values that we have. So if we will open this one, like there exists p of x and this one will be having various true false false true values, truth values. Along with that we will do OR of q, so like true false false true, this will result to true even if we need only one among this as true. Similarly here if we will open, it is ultimately we are doing OR on both the sides, so they are equivalent. Similarly for AND condition, that is for all x. In for all we always do AND. So when we are doing individually, like here we can write common, take this one common and do.